Okay, class, continuing on with 14b problems. Let's get started with number 60. It says, what is meant by the term molecularity? Molecularity, you see I have an example here. The example is H2 plus O2 yields H2O. After I balance the equation and I end up, there we go, with a 2 in front of the H2 and a 2 in front of the H2O. And as far as molecularity is concerned, none of this makes any difference after the arrow. All it is about what's going on in front of the arrow. So once I balance the equation, I can ignore the products completely. And here I have 2 hydrogen molecules and 1 oxygen molecule. That would be 3, which means termolecular. Okay, termolecular means 3 things. It doesn't matter if all 3 are different molecules, if all 3 are the same molecule, or if there's some combination of 2 of them are the same and 1's different. So that's question A that says, what is meant by the term molecularity? Molecularity is the number of molecules that react in the reactants. So that would be termolecular for this one. If there's only 2 of them, that would be bimolecular. And if it's only 1 reactant molecule that's decomposing, that would be unimolecular. Okay, so why is termolecular so rare? Well, it's just not when you have 3 molecules, they all have to hit each other, collide. Collision of 3 molecules is just very difficult, and having 2 molecules collide and oriented in a way where the bonds break and reform is tough enough, and to have 3 do it is almost impossible. So collision of 3 molecules is very difficult. Oops, there we go. That says difficult. Is very difficult to have the correct energy and orientation. That's what it comes down to. An orientation to break bonds and reform. Okay, good. So that means that 3 molecules come together. That has to break, that has to break, and that has to break. And then we have to form new bonds here and here and here and here. And that's just not something that happens very easily, especially with 3 molecules. It doesn't happen easily with 2 molecules. So let's scroll down a little bit more. The last part says, what is the intermediate in a mechanism? I'm going to show that to you. The intermediate is something that gets produced on this side, and then the intermediate then gets used in the next. So it's like it shows up as a product, and then it goes away as a reactant. The reactant gets used up then. So you never really see an intermediate when it's like when you finally figure out the whole equation. And we're going to take a look. I'm going to identify what an actual intermediate is in number 72, which is coming up. So let's take a look at 62. What is the molecularity of each of the following elementary reactions, and write the rate law for each. So this one is bimolecular. There are 2 molecules. Obviously for this here, so this would be bi, and the rate law would be K times NO, and because this is an elementary and there's 2 of them, I have a second order. Okay, so let's keep going. This would be unimolecular, and the rate law equals K times, and what is this? There's 3 C's, C3, and how many H's? 6 H's. Oops. Bonehead. Like this, and because there's only 1 of them, there's a 1 for the first order. So the last one, again, is, there we go, is unimolecular, And the rate law then would be, if I wrote this down correctly, SO3, like this, to the first order. Okay, and that's it for 62. Then we jump to 72. Now here's where I'm going to show you an intermediate. I wonder if you can pick it out on your own. Notice we got NO plus N2O yields N2 plus NO2. And then over here on the other side, NO2 and NO2 react to form some more stuff. So one of these NO2s is an intermediate. Okay, that's what an intermediate is. Feels like there should be two M's there. I don't know. Okay, intermediate is the NO2. Notice it's produced on one side and taken away on another side. And that's what an intermediate is. Notice that this says NO is catalyzed. NO catalyzed in a decomposition reaction. So that means that what I have here then is a catalyst. What's the difference between a catalyst and an intermediate? Notice what happens for a catalyst. Catalyst shows up in the beginning and the reactants and then gets used up and then produced again at the end, which is why that's a catalyst. Notice that goes from the reactant of one mechanism to the product of another and is not used in the reaction then. Okay? So let's keep going so we can figure out what's going on with letter A. Says what is the overall reaction for number 72. So the overall reaction looks like I'm going to have to double the first one. So I'm going to double everything that's inside here, which means times, if you double the whole first elementary reaction, then it doesn't change anything. So we got 2, 2, 2, and 2, like that. Okay? So when I do that, then notice what I can do here. The NO, I cross off here, there's two of them, and I have 2 here. So if a compound shows up on the left-hand side of one reaction and the right-hand side of the other reaction, then I can get rid of it. I can just cross it off then. So here I have NO2 and NO2, there's 2 of them, plus I have 2 of them here. Now that leaves me with, after I go through and get done crossing off stuff, then I'm left with these then, like this. So I got 2N2O form 2N2 plus O2. And that should all be balanced. Then it is. I get 2 times 2 is 4, and 2 times 2 is 4 for the N's, and 2 times 1 is 2 for the O's, and then 2 over there for the O's. So that's already balanced. So there is my equation that does not have any intermediates or any catalyst in it. There you go. Okay, letter B for number 72. 72B says, why is NO considered a catalyst and not an intermediate? Okay, I think I answered that one already, so I'll just say it verbally. NO is a catalyst because it's in the beginning of one reaction, gets used up, and then is at the product of another reaction, which means that it basically went through the reaction unchanged. So that's what a catalyst is. So if experiments show, this is letter C, by the way, for number 72. If experiments show that during the decomposition of N2O and NO2 does not accumulate in any measurable quantities, does this rule out the proposed mechanism? Let's take a look. If you think not, suggest what might be going on. Let me read that one more time. If experiments show that during the decomposition of N2O, NO2, okay, is on the right-hand side, does not, that's the intermediate, does not accumulate in any measurable quantity, does this rule out the proposed mechanism? No. No, it doesn't. And here's why. So it's saying if the experiments show that this part here, let me get rid of some of this stuff so that you can see what's going on. Excellent. Now, so that means, what if this compound right here, the intermediate, is not showing up a lot? Well, that means that I'm producing the NO2 slowly, okay, and then using it up over here fast, which means that here I have a situation where the N2 and the NO2 are being produced slowly, so this is my slow step. The first step is the slow step, and then the second step is my fast step, so anything that's produced that's NO2 gets produced quickly and is gone. So we don't really ever see the NO2 because as soon as it's produced in the first reaction, it's taken up and used in the second reaction quickly. So my slow step is the first step, so that does not negate the mechanism that we have here. Okay, so this goes back to the whole slow step, this part right here. So what I have is this on the left-hand side, where the first step is the one that holds up the reaction, and then notice that these cars here then can easily just keep going through plaza B in this direction because that's the fast step. So slow step first, fast step second would be exactly what letter C was describing. Nice work. Hope you've enjoyed this screencast. Talk to you later.